So we are going to cover today introduction to STD variant, STD any, and its practical applications as well. We'll see two problems which we can solve with STD variant and another with STD any. So let's just start with the agenda. So what we are going to cover today, we will just go through unions and what problems we have with unions. Then we'll have a long walk through STD variant. Then we'll go through the details of how STD visit helps us to write a better code. Then we'll go through STD any, and then at the end of this session we'll see two problems. One is implementing finite state machines using variants, and implementing a simple config manager using standard any. And at the end of the sessions we'll see what are the considerations we should take into account while using STD variant and STD any, that might be related to execution time, that might be related to the memory footprints. And at the end, if time permits, we'll have a question and answer. So if you have any questions in between, please feel free to drop into Q&A option. If you don't see Q&A option, you can put it into a chat as well. And after particular intervals wherever I see a logical ending, I will wait for some questions and we'll take some questions there. Okay, so let's start with revisiting unions. We know that unions were introduced in C itself, and they are very useful where you want to store a multiple, where the value of a data can be of any one of the known type at a certain point of time. These are also very useful in low level operations like memory manipulation and that. The major problem with union is its undefined behavior to access a member which is not recently written or which is not active, we say, right? And union by inherently doesn't keep track of which one is the active member. So as a programmer, you have to keep track of, okay, what is the type of the member and which member is currently active. So let's take a simple example here. Let's say we have a union, and we have some basic data types in the union, and you can see, right, the first A takes a 4 bytes, second takes a 2 bytes, the double takes 8 bytes on 64-bit system. So let's go with the 8 bytes. The overall size of the union will be 8 bytes, and if you are writing to A, then and if you try to read from C or B, then it is undefined behavior. So you can see very simply here that here when I am writing U is equal to U, because of the designated initializer, the E will get because of the initializer, A will get initialized to 100, and then you can access E. And let's say what I did on the line number 18, I have assigned value to C, which is double 3.14, and if I try to access C, and that's fine, perfectly fine. But if you try to access A, standard says it is undefined behavior. So when it is undefined behavior, anything can happen. Anything in the sense compiler are free to optimize the codes. And so basically unions are not type safe. Why they are not type safe? Because they lacks tracking of the active member. Another major problem with the union is it requires a special handling if you want to switch a data members where the type of the members are non-trivial, where the data member have a user defined constructor or destructors. So let's see with an example. So let's say we have union with two members, one is string and another one is vector. Now as union doesn't keep a track of which one is the active, when you are switching a member, let's say, in that case union doesn't know which destructor to call, right? So we may have to manually call a destructor, or we have to manually call the constructor for the construction of the next variable. So you can see here on the line number 14, I'm initializing the union S. This is fine. But on line number 719, if we see, before changing it to a vector, I have to basically call destructor manually. And even while initializing or switching the data members to vector, I have to use this placement new operator, right? And this is basically a very tricky part. And yeah, and even if you can see at the end, before yes goes out of scope, we have to explicitly call the destructor, because the destructor in the union doesn't know exactly which type it is holding and which destructor it needs to call. So this is a basic problem with the union. So to solve all these problems, to solve the type safety on all these issues, in C++ 17, STD variant got introduced. So STD variant is also called as a discriminated union. Some people call it a tagged union. So the very simple principle behind the STD variant is that it can keep the track of what is the active member. And as soon as you can keep the track of the active member, then a lot of other door opens for you. Then you can implement type safety. I mean, if you want to access a particular member, and if you are saying that give me a int value from that one, you try to match, okay, whether the active member is int, or whether it is string, or whether it is something else. And if the active member is not matching what you are trying to access, then you can throw an error. That error might be exception, or there might be different ways to handle that error conditions. So that what the STD variant is for us. So it is a type safe union because it tracks the active member. Again, like a union, it is designed for fixed set of known types. So you can't have like everything there. Another good thing about union is the variant is data is stored inside itself without extra memory allocation. So you might be wondering, these are exactly same points with the STD variant, then why we are listing down here. But when we'll see STD any, then we'll see, okay, what is the problem with these points, and how it plays role in the STD any. And once we default construct the variant, then it holds the first alternative. So when we say alternative, it is like what are the types allowed. So whatever is the in the declaration order, whatever is the first we have specified, that will get value initialized, right? For example, if you are int, then it will get initialized to a 0. Let's say you have some user defined data type and has a default constructor, then you can consider its default constructor will get called and it will get initialized. So STD variant will always, I mean, will have initial value itself. Okay, you might be saying there is a small star there. I have put, let's say, terms and conditions apply. So the condition here is, let's say you have your first data first type itself, which doesn't have the default constructor, or I say that constructor without parameter. You need to pass some parameters to initialize that one. In that case, this can't be default initialized, and for that we have another provision called as std monostate. We'll see that into upcoming slides. As variant keeps track of what is the active member, it doesn't need any special handling for non-trivial data type as well. You can hold, so it is permitted to hold the same type more than once, and you can also have the const volatile qualifiers. So you can have int std variant of int, not sure what might be the practical use case of that one, but yeah, you can have that. Or you can have, let's say, one int and another is, let's say, constant, something like that is possible. What is not possible in std variant is to hold the references or to hold the c style arrays or void type. So that is not permitted. Definitely we can hold std vector, we can hold std array, all these are allowed, but not c style array. So let's go through some construction functions which we can use to initialize the variants, and how do we declare the variant. So the declaration of the variant is very simple. You just say std variant, and like a templatized parameter, you pass what are the alternatives which are allowed. So for example, in this case, if you see, we are creating a variant which can hold int, double and string. Now it will get default initialize with the value 0 because int is its default initialization is 0, right? And in case of value initialization, you explicitly provide the value and it will try to match with the exact type. Let's say here int and double. 10.5 is a double, it's not a float, right? If you want to have a float, it will be f. And let's say if you have int, float and double, and if you say 10.5, then it will get initialized to float, otherwise it will get assigned to double, right? So it tries to match the type. Let's say in case where I have just, I said, we can there are cases where this conversion is not possible and compiler is not able to detect exactly which conversions need to be done and which one of the alternative to pick. In that case, we explicitly can say, okay, at which index this needs to be initialized. I mean, for example, let's take a third example here, in place initialization using index. So here, what we can pass as a first argument is std in place index and the index number. So in C++, everywhere the index numbers are 0 base. So here also it is a 0 base. So when we say 2, then it will get initialized with the float. Even though 3.14 is now double value, but we are explicitly stating that, okay, you invoke the constructor of the float and you assign that value to float. So the active member now is basically a float here. So this is std in place index. There is another in place initialization possible, which is using a type. So we can specify in place type, right? So here I am specifying in place of float, you initialize 3.14. Let's say if you have two floats, let's say variant of int, float, float. In that case, it will not be able to distinguish which float to take, and then it will generate a compilation error. So in that case, you have to explicitly use the index. The another one is using initializer list. So let's say you have a alternative data type which takes an initializer list as a part of a constructor, and then you want to pass that. So then you can't directly pass it. You have to basically use the in-place syntax. That might be in-place index or that might be in-place type. At least one of them you have to, any one of them you have to use. You can't directly initialize. So in this case, for example, we have this std vector of int, and I want to initialize this vector with these three values 1, 2, 3. So in this case, I have to use this in place index syntax, and that will get initialized properly. So I was talking about that what will happen if our first alternative type is it doesn't have this default constructor. I mean, when I say default constructor, it means it doesn't it needs to take some parameter to initialize this one. In that case, you will not be able to initialize, you will not be able to do default initialization. For example, the syntax on line number 13 will give a compilation error because this struct with which we want to initialize takes integer as a parameter. So for such states, C++ has provided a nice utility called as a monostate. Monostate is nothing but you can say an empty structure, and empty structure can anyhow be initialized. So you can just say std monostate, and as a first parameter or first template argument, then in that case this will become the first, this will become the second and third, and when you initialize with the default initialization, basically variant 2 will now contain monostate value. Okay, so any question till this point? I saw Sachin raised hand. Aspersh.
Like I wanted to ask, like if like STD monostate, not variant, but STD monostate is it C++17 as well?
Yes.
Okay, and I think I have another question, but like I would like the answer of it at the end, which is like if I'm using a lot of unions, not one union, but I have a lot of unions. So and since they are templatized, so is there some performance cost, like overhead cost, like I would have to suffer because since I'm using a lot of unions, so compiled like
Okay. We'll then talk it
in
at
the
the end.
end, in the end.
Okay. Dheeraj?
Yep, I have a question related to this monostate only. So you said monostate will have it's a empty structure, right? Uh, so is it that variant when we initialize a variant, it initialize the first element only? If let's say I'm not giving any in place type or anything, it will initialize only the first element, right? So
If you are not even passing any value, for example, something which is written on line number 16, where I'm not even assigning any value, right? So it will definitely initialize the first one,
okay.
and in this case, it will be monostate. I mean, you can just say that okay, we are creating object of empty structure.
So this monostate is only for these kind of purpose. Means it's somehow we are fooling compiler. Okay, you just skip this part.
Yeah, it is just a utility. I mean, it is
Okay,
not some standard language feature. It is just an utility. Yeah.
okay, got it.
Yeah.
Mahendra, can it be thought this monostat as an optional thing in the way, like when we use it with variant and optional, like basically if it's an empty,
Mhm.
so you are not basically storing any value kind of thing.
Yes, we are not storing any value, and then now if you query variant2 dot has value or variant2 dot get all these things, it will return monostate. So you can consider, let's say if monostate was not there, how could you have handled this problem? You might have shifted bool on the other side, right? Let's take a case where you have all the type parameters which take something as like a parameter. Then what you might have done, you might have initialized with the value, but let's say you don't have that value as well in the initialization, then you could have defined some empty structure and use that empty structure as your first variant, right? Alternative variant. So that's it. It's nothing fancy.
Mahendra, on similar line, I was thinking that it's good to get that error, right? That you are supposed to provide something for initialization,
Um,
isn't it?
you're right, but see before, I mean C++11, that whatever the types we have, let's say int, if you don't initialize it one, then it has a garbage value.
True.
But that's not case with the std variant, right? So you know that std variant will invoke the default constructor of the first alternative even if you don't specify. So it's a valid state and it's selective method as well. Sometime you might not have the exact value to initialize at the program, right? Then you need to introduce some dummy values just to satisfy all these constructs. So that's why we have this alternative.
Okay.
There is someone, Shorfa Isam.
Yeah, good morning, everybody. So I have a small question. This example, if you try to build it with another type of compiler like a Glank, I don't know, but I'm sure that he will be, I'm not sure, but maybe he will be generate a default constructor for the structure S, and here the std monostate will be useless.
No,
No,
because once
because
you
once you
getting echo.
getting echo. Yeah, I will cut my mic. Okay.
So once you define your own user defined constructor, then the default constructor is basically deleted. So if you try to compile it, will say that deleted constructor. It will not generate once you specify the constructor on line number 6, right? Then it will not generate default constructor.
Okay, thanks.
Okay, so let's go further. So let's see some accessors and modifiers of the std variant. So what there is in place, and then there is index, hold alternative, which basically to query the things, in place to modify, variant size is to what is the size of the variant, and what is the type of at a particular index. std get and getif is to access the values, and valueless by exception I think I haven't covered, but yeah, I will cover. There are some cases where variant might not have a value because of exceptions occurred at the time of the initialization. So you can query by using this function that okay, whether it is having some value or not, right? So let's see with examples directly. So let's say in place. In place is to modify. It provides almost all the facilities which is provided by all these different types of constructor. So once you created a variant and then now you want to change the active member, so basically you can say in place at a particular index, or you can say in place for a particular type, and you can even pass a initializer list as well. And if you have two std strings, let's say, then to resolve ambiguity you always have to use the index, otherwise it will say that okay, it's ambiguous error if you try to use the type. So very simple syntax, and it will construct the object directly at the memory. Going to next one, queries. So on the query side, we have index which returns zero base index of an active member. So let's say if you have 5 or 6 members and the second or third is active, it will return that number to you. std holds alternative checks if a variant currently holds a particular given type. It returns true or false. Variant size v returns number of elements. It doesn't return the size of the variant, right? So number of elements in the sense how many alternatives are possible with this variant, and this is at compile time, so very useful while doing let's say template meta programming. Variant alternative allows you to query a type of alternative at a given index. We'll see that with examples. So for example, we have this variant where once again I'm using the same type of structure in double and string, and if you query the index, by default, as I said, it will get initialized with the first one, so it will return 0. If I switch data members, now 42.5, it is double, so if I now once again query index, then it will return 1 2. By using holds alternative, I can pass a templatized parameter and check whether the variant holds the double value. If it holds a double value, it will return true. If it doesn't hold a double value, then it will return false. So you can do a basic type checking here. Then we have this variant size v, and if for this we have 3 alternatives available, so it will return 3 only, right? And then to query a particular type here, like what is the type at index 1 or index 2, we can use variant alternative t. This is short form. You can use std variant alternative colon and all this, and after that type. This is basically type trace shortcuts which is available in C++17. So we can have the type, and we can see here I'm at the compile time, all these type traits are at compile time checking that okay, whether this variant holds double at index 1, right? Using the static assets. So these are the queries functions. On the accessor sides, we have get and getif. So basically, what is the difference between get and getif? Get will return you the queried value if your variant holds that type, otherwise it will throw an exception. Whereas getif will return you the pointer to the underlying value if it is holding that one, otherwise it will return the null pointer. So both alternatives are possible. If you don't prefer to use exceptions, you can use getif. If you prefer to use exception, and you can use get. Even you can use get. Basically, you initially only check with the holds alternative that okay, whether in the if condition whether it holds a double. If it yes, then you query get using a double. So that That way you know that okay, it will not throw an exception. Let's see with the example. So let's say when I try to get it to the end, because I know this initialized with the end, I can get it. I can pass index as well, that okay, pass me a 0. So let's see, if I pass 1 here, then it will throw an exception, because it is not holding the basically the active member is not of whatever is present at the index 0. So it will throw an error. And let's say how we can use get if. So if we see in the get, we pass actually the variant, basically we pass the reference, but whereas in the get if, we pass the pointer. So this is the difference. And basically it will also return a pointer. So if it is holding a double value, then it will return me a non-null pointer, and I can basically modify the value directly there of that by using that pointer, right? Because it is not changing a type, so it doesn't matter, right? It's not switching active member because we are assigning directly the same value here. Here also we can use the get with the type and it will not throw an error because we have checked it already. And then let's say I was talking about the exception here. The active member now on line number 18 is switched to std string, and if I try to access it with the double, it will throw an band variant access exception. Even if you use, let's say, indexes and indexes like out of bound, if you use 3 here anywhere, it will throw an out of bound exception. Okay, I mean, and the bad variant access exception it will throw. So this is with the accessors. Okay, any question on the queries, accessors and modifications? Otherwise we'll go to std visit. Okay. So let's say, so this is my favorite utility, std visit. So it basically implements visitor pattern, right, on variant. So it works like that. For example, you will have this visit and you will pass some visitor here, and this will get called on the whatever is the active member of a variant, right? So you need to pass a visitor here in such a way that it accepts all the combination of this variant. So what I mean to say basically is, let's say you are holding std variant in the variant you are holding int, double and string. Then you have to pass a visitor or callable here such a way that it accepts everything. It can accept int, it can access std string, and it can access it can accept a double as well. So how we can achieve that? We can achieve that using templatized function. We can achieve that using generic lambdas, or by passing auto as a parameter to the function after C++20. We'll see that with example. So here you can see I can pass multiple variants as well. So let's say I'm passing a 2 variants, each one of is holding, let's say, 3 alternatives. So the total number of combination is now a cross product 3 into 3, which is nothing but 9, right? So I need a visitor here which can accept all these 9 combinations. So we'll see example of both. So we'll go very slowly with this one. Let's see a simple example of variant once again in double string, same value as a 42. And I just want to print the exact value. So the interface is common one. So as the interface is common one, I can write a single function, but which is a generic function basically. So I can use a generic lambda here and directly do a cout. Generic lambdas are nothing but we know it is a kind of a syntactic sugar on top of the function objects. So we can very well write our own structure, print visitor, we can overload operator, and then we can use templates here to write the generic code, and then it will basically and we can instantiate it here, and it will call. So both will kind of the same one. So how STD visit internally works, and that we'll see once we implement the FSM, and that we'll go into the details how it is able to call up this visitor for a particular data type, even though let's say signature might be different in that. Let's take another example. So here in this example, I was able to use the same function because the interface is same. I mean, let's say this argument I can print with stdc. Let's say I want to calculate something like a area now, right? And very well I can have an area function here which can directly give me a value, but let's say I don't have that privilege, or let's say I have some types where the interfaces are not same on that variants, whatever thing which I want to do. For example, let's say I want to double the value of whatever is the holding. So, and I'm holding int double, let's say, and int double and string. So I can multiply for int, I can use multiplication operator for double, but for string I need to use a string concatenation operation to make it, let's say, double, right? So the interface is different. No, I can't use something like this generic lambda or something like this on a single function. So I need multiple functions here. Correct. So let's see an example with this very toy example. Once again, we have, let's say, two types, a circle and radius. Sorry, circle and square. One is holding radius, another is holding side length, and the formula to calculate the area is different. So it's saying that okay, the interfaces might be different. Not very good example, but yeah, it conveys message. Now we have created a variant, shape variant, and now we want to calculate area. A very simple thing what we can do is we can write our a structure area calculator and then can overload operator here, right? What with one type as a circle and another type is a square, and then both are retaining the same value double, so should be fine, no worries. And then we can directly use this area calculator into the STD visit by instantiating, and then it knows whatever is the current active member, it will accordingly call that one. For example, here it is a square, so it will print the area of the square. If it could have been circle, then will do a circle. Right? Now the problem with the, let's say, lambdas, because in lambda we can't overload now this operator, right? I mean, we only have one thing. So let's say I want to build all these visitors on the fly. I mean, so then I can use lambdas. But then how to use lambdas in such cases? So let's take an example. So I can write a lambda, and now this code look like much more to view on a slide and ugly, but it's a very simple code. So I can write a simple lambda, which is taking some auto parameter, which is generic one. Then I can basically use if const expert to check whether the type is circle or whether the type is square. And if it is circle, then I can basically use the area calculation of the circle. If it is let's say square, then I can use a square. You can say, you know, if you have some different other APIs, then we can call that APIs here as well. And this is just for, let's say, for non-exhaustive visitor purposes, just that okay, we are not missing anything, so we can use a static asset here. If it goes here, then we know that okay, our variant was holding something more which is not circle and square, right? Let's say tomorrow we implemented something like we added a new thing, polygon, but we missed to add here, so we can always have this non-exhaustive visitor condition. And now you can add a calculate area here. This looks okay for a very small function kind of thing, even though with this small one it looks ugly. I mean, the code for circle and code for square, everything is mixed up. What I want is to have different lambdas for different calculations. Let's say I want to have a separate lambda for calculating the area of circle. I want to have a separate lambda to calculate the area of square. Now what I have to do is how to fall back to the same mechanism, right? Overload the operator, because I can't overload the lambda. But can we generate such a structure on the fly, right? By using a template metaprogramming or some technique, right? So that's what we are going to do in the next slide. What we are going to do is basically don't focus on till line number 7. So we have these two lambdas. One is on line number 10, another is on line number 11, and then we have this such a helper utility, let's say overloaded. This is not part of a standard. It is defined in 2 lines above that. We'll explain that as well, which will help us to create a structure like the one which was there, right? And how it basically creates it. If you see a definition of overloaded, so whatever I am passing to this overloaded, basically this is a lambda which is in turn, let's say, a function object which is nothing but a struct. So what I am saying is you inherit from it, and I can pass any number of arguments here because I'm using the I think it's called as full expressions, and I can basically use pass any number of, and then this overloaded will get inherited from the all these lambdas, right? And then in that overloaded, what I am saying, you use the operators, make it visible on the overloaded one. So at the end, what I am doing, I am instantiating this overloaded one only, right? And then all these overloaded lambdas are part of this overloaded structure, right? I mean, don't worry too much about this. You can directly just copy paste this and use this one. There is a proposal also to take it into a C++ standard, but it's not yet accepted as per my knowledge. It's not part of C++20. In C++70, you need something like this. This is called as some deduction guide and that, but in C++20 you don't need. Basically what we are saying that when we are passing all these parameters to the overloaded, then we are saying that okay, what to deduce from it, right? So it will work like a charm, right? Now you can have different lambdas. So that's it. What was std visit? Any questions? Okay, so let's go to std and then we'll see examples. We have a few minutes left. So we saw std variant, it can hold known types, whereas std can hold any number of types, unknown type. So it is the replacement to white star, but it is a type C. Internally, std might be even using a white star, but we don't know what might be the implementation, but the simple implementation might be okay, use a white star in the internal implementation and keep track of what is the active type, right? Because what is the problem with the std, I mean, what is the problem with the union or white star? It doesn't keep track of whatever is the active type. So if you just add that possibility to keep track of active type, then we are done. So that what std does, it keeps track of the active type. As I mentioned, what it I was talking in the std variant that it doesn't allocate memory dynamically, but std can allocate a memory dynamically. So if you are working on some, let's say, resource constraint, you don't want to have dynamic memory allocations in that, then you need to really think whether you want to use std or not, right? Once again, let's see a construction. It is very simple as compared to std variant. You declare std a1, and now with std variant we had option that okay, we could initialize it with the first type. Here we don't have any option, so this will not have any value. And there is a method you can check whether the variant is the any is having a value or not. Same thing like optional, we can check whether it has a value or not. And then you can do value initialization. In this case, a2 will have basically int. In the case of 3, a3 will have any as std vector. Now here what we are doing, we are creating object here, and then we are passing that might get copied into our dynamically allocated memory. So if you just want to directly construct it there, so you can use the in place initialization. So you can use in place initialization and you say okay, I want to construct std string and pass here the string, or you can make use of std make any. It's something like std shared, right? And it will construct this object directly inside the allocated memory. Accesses and modifiers, very simple one. So we have this any cast. So by using any cast, if you wrongly pass a cast here, it will throw an exception. As simple as that. So let's say if a1 is now here integer, if I try to use double here instead of int on line number 3, it will throw an exception to me. But now in this case, if it is directly throwing an exception and we don't have any other information, right, the way we had index invariant or holds alternative to check before querying that value. So what we have here is std any returns a type id, or basically a type information. So what you can do, you can directly compare it with the type id. So you can query, let's say e1 is my variant, e1 dot type, and then you can say okay whether its type id is matching with the type id of double. And if it is, then it is safe to do a std any cast, then it's not going to throw any exception. Otherwise it's going to throw an exception, which is nothing but bad any cast, and you can handle that exception, but at least it guarantees the type safety. Right. So where can we use, wherever we are using void star to store this all different types of data, we can safely replace that with the std. Okay, so the as we had a similar thing in the std variant, that we had two options, either we have exceptions or we have a null pointer getting written there. Similarly here we also have the both the thing. Same syntax in there in the gate. What we are passing was a variant, and get if we are passing pointer. Similarly here on the any cast, if you pass a pointer, it will return a pointer, and if the pointer is null pointer, that means whatever the type you are querying is not matching. Yeah, that's simple. In place is again same. There is another method called as a reset, which will basically call the destructor on the underlying type, and then now even will not hold any value. So I can once again check with the has value. So these are some accessors and modifiers. Any questions till this point? If not, then we'll directly go to some practical examples of std any and std variant. Okay, so let's see implementing FSM. So there are many applications where std variant can be used. One of them can be, let's say, okay, some command line parsing, that way we know that okay there is a one option, or the generic command line parser that we know that okay if number is passed, then I want to store it, let's say some larger value integer. If some string is passed, I want to store it as a string. If the comma separator values are passed, then I want to store it as std vector of the underlying type. Then you, if you know all these data types, then you can use std variant and implement a generic command line parser, or you can implement generic command um, generic file parsers, config parsers, and all that things. The very interesting thing which I have found by using std visit is you can implement FSM very neatly. So I'm just going to talk about the FSM and not about other applications. So let's say about FSM. Okay, sorry. Yep. Hope you are able to see code and it's readable. Okay. So we'll go a step by step. So what we want to implement is a state machine for our ATM machines, and have simplified it. When we are not implementing any function logic, we will just focus on the transitions. So let's say this is our very simplified ATM machine where our initial state is idle one, and if you insert a card, then it will get into card inserted state. We are always saying that okay whatever is the card, it's a good card, and once card is inserted, then if you enter a pin, then we go into pin enter state, and we know that customer is very good and he always will enter a correct pin. So we are not checking all these corner cases of incorrect. And then once the pin is entered, then we'll process for transaction. Okay, whatever amount of money he wants to do, the ATM machine has a large cash reservoir. It will basically dispense all that amount, and whether the customer has that amount in his account or not doesn't matter. Okay, and then once the transaction is complete, customer can a remove card and it will go once again into idle state. That's what the simple thing we want to implement. So before looking into the code, I mean, if you want to implement the FSM, generally the way we implement is using the enums. We create enums of events, we create enums of states. Then we have some function called as a process event, where that function take in account whatever is the current state and whatever is the event, and whether the transition is valid transition or not. If it is valid, it checks all these things, call some specific handlers if you want to, let's say, modularize the code for each every this event type, and let's say state combination, you can have different handlers. If you want to make it more, I mean, simplified, and that what you can do, you can create an unordered map of, let's say, where the key is state, key is, let's say, pair, which is state and event, and the value is nothing but the handler. So you don't have to write the function, and you don't have to maintain the switch cases, and that is basically query, okay, this is the state, this is the event, and then you give me the handler, and then we'll directly call the handler. That is possible. But what is not possible with the enum based state machine is that, let's say, my every state has a different attributes, or my event has some different properties. For example, in this case, I haven't again covered, but let's say in the case of card inserted, the cards attribute, like, okay, the name, number, type, and that card be a uh, let's see, a property of card inserted, not like I don't have to store it anywhere else, that is tied with the card inserted. Let's say for the event process transaction, whatever the transaction amount I'm entering, that is a part of that event. So to implement these things, what we do in enum based one is we create another structure called as event, and in that event we underline, okay, say that, okay, whatever is the current event and whatever are the possible different attributes are associated with all type of events, we declare it there. So it might be, let's say, for example, we have let's say a pin entry event and a process transaction event. Let's say with the pin entry event, pin number is associated with the process transaction event, the amount is associated. So we'll create a, let's say, some structure which will have event, which will have the enum event, and it will have, let's say, some integer based value which is the pin, and another integer based value is the transaction, the amount requested. Now the problem here is, once we are accessing that event, we need to know that, okay, with which event which values are valid and which are not a valid one. Same applies to state. A particular state might have its own attribute, but what we generally do, then whatever our attributes are for that a particular state is available, we apply that into, or declare that into the complete class, right? So we lose the type safety there this way. But when we are using the variant based mechanism, what we can do, we can create the states as a structure and event as a structure, and then we can have anything associated with the structure. You can create a class as well, anything is possible here, right? And then you can have all the attributes associated with that. You can have some helper function associated with that particular event to return a particular information. So it is neat and clean. So the way I have implemented this is basically created states. Now you can fill up the information, the empty braces, whatever you want, and then have the events as well. Then in the ATM machine, I have created a state variant which can be idle, card inserted, pin inserted, transaction complete, and the event can be any one. And the state is internal to ATM machine, and event is coming from the outside. So we have defined this process event function, which will basically take the event, and based on the current state, it will call the particular handler. So if you clearly see here, I am using std visit pattern once again, and I have something called as a on event as my state. And if you remember that I have told that with the std visit you can pass a multiple variant. I'm passing here current state and event. So how many combinations are required? Total is 4 in the state and 4 in the event, which is nothing but 16 combinations. So I require the 16 combinations. So when state is idle and event is card insertion and state is idle, all these 16 combinations are required. Okay, and out of that 16, there might be 4 or 5 only which is valid combinations, and other are like invalid combinations. So let's see how we can handle this one. Let's first talk about valid combinations only. So what we can do is basically, so I have written this on event function, and as this event is structured, right? So then I can overload it. I can't overload it based on the enum. So I can have an on event function which is overloaded on, which takes state as idle and card insertion as an event. So I know when my state will be an idle state and my event will be, let's say, card insertion event, then this function is going to get called. I don't have to write that switch case statement to do this one because std visit is doing that for me. How it is doing, we'll see it. Similarly, I have written for, let's say, card inserted and then event is pin entry and let's say all the valid state I have listed. And for all other invalid state, I can write a simple generic function that can be templatized based function, or in C++20 you can directly write atto as a parameter, which will take all other cases. The precedence in the overloaded resolution is for these functions, directly defined functions, and this has a low precedence. But if it doesn't match, then it's going to call this function, and then this function is basically, it will get called on invalid state. So let's say tomorrow you want to add some new entry in this transaction table, in this table. What you just have to do, you have to just define an on event function with that as a state as a and event as a parameter. You are done. There is a no change required anywhere. It's as simple as that. And I was talking about, right, let's say when I'm processing now here pin entry event, I can query from the pin entry event what is the pin, and I can very well check whether the pin is valid or not, and if it is not, then I can return to some invalid state, or I can ask to go back to a pin in card inserted state only and once again enter a pin. Similarly, with the transaction complete, the transaction process transaction, I can query that, okay, whatever is the amount associated with that one, and I know that because it is a process transaction, whatever is the amount it will become, it is valid, and it's not in invalid state. So this is possible, and it is a very simple simulation where event is card inserted, pin entry, process transaction, and card removed. I can add some invalid entry here. Let's say if I just say card insertion here instead of card removal, here on this side you can see basically it's saying that, okay, invalid state. All these functional aspects then you can implement, but this is I think a very simple one. Now let's see how, I mean, I was curious when I saw std visit. I was curious that, okay, how this std visit is basically doing this dispatch on event at runtime. See, this is not a compiler, this is runtime, because this event can have anything. So we know runtime polymorphism can be achieved using virtual tables only. But how std visit is doing it? So if you see, the implementation is up to the toolchain, but toolchains like GCC and CLang prefers to write it something like generating a table, whereas MSVC somehow converts all these things into a switch case statement using type ID and all these mechanisms, and they generate it. So if you see, I just wanted to show where is the complete table is generated. So I'm hoping that you are able to see this table here. You see here, code, and all this, and it is having all this information, which handler to call, and that it's too long to scroll even. But okay, it has generated this table, and if you count it, this should be a 16 only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Correct? It has generated all these 16 operations. So whatever the remaining combinations were there, it has generated that remaining combinations using the const at O. Right? It has instantiated that one. So this is how the std variant works internally, and this is how we can implement a FSM. Okay. Now I'm not going to take questions because we have very limited time. We are already shoot like 13 minutes. I want to cover one more problem, which is nothing but using a config implementing a simple config manager. That's what we saw in FSM. Okay, I'm not going to zoom it slideshow because I just have to show this one. So implementing a configuration manager using std. Now we can implement a configuration manager using std variant as well. And if you know the types already, then prefer std variant or std. But if you don't know the type, then okay, definitely you can't do anything. Then you have to go with the std. and here is a sample implementation. It's very simple implementation. What we have done, we have created a here heterogeneous container, right? So you can use underlying, see, application is a configuration manager, but what is the underlying implementation? Heterogeneous container. And now you can use heterogeneous container in a multiple implementation, different types of implementation. This one is a configuration manager, right? Another is, let's say, JSON parser kind of thing. And I mean, there are much more like this. So what I am doing here is my key is std string, whereas the value is std any. And now I have these two simple functions. One is a set function, another is a get function. What set function does is whatever the value you specify, it just adds into this map, an ordered map. And while getting that one, it queries that, okay, whatever the type IDs are there, are that good or not? And if it is not matching, then it basically returns a null opt. Basically, I'm returning optional value here. So what I am saying is this get function might not return you a value as well, because let's say that configuration itself is not available for given key, or the type is mismatched. So in that case, it will return null. Now we can use a very this is a toy example, but whatever the configuration manager you see here on top, this is a real code example, very simplified version though. And here I can see the, okay, configuration manager dot set. I mean, you can parse a configuration file and then invoke this function, and I'm saying, okay, username, maximum number of connection, and then I can query this, right? Okay, username. And now here you see I am using this value, or this has nothing to do with the std any. This is coming from std optional, right? If std optional now returns here a value, then it will return me that value. If it doesn't return me a value, it returns a null op, then this is a default value. And sometimes it happens that we have some configuration manager and we know what are the default values, so we can say, okay, return value if it is set or not. So this is so much readable, right? You can say value or something like that. So this is how you can implement a simple configuration manager. You can use std. And our last slide of the talk, and then we'll go for questions. Yes. So let's see what are the performance consideration while using std or std variant. So in the case of std there can be a dynamic memory allocation happening. But what standard recommend is that, okay, for small objects like integer, float, and some small strings, it basically don't go and create a or do a dynamic allocation, but you basically try to use a small buffer optimization technique, which is heavily used in the std string as well. But as soon as this technique needs to be used, you need to have some reserved buffer space, right? I mean, let's say if you said, okay, for if the type is of 8 byte only, then I will use the local buffer, otherwise I will go for heap. So eventually what will happen is, based on the compiler implementation, the footprint of std any, I'm not talking about dynamically allocated memory, the footprint of std any can be a huge one. So some compiler I have seen it's 16 byte, and some compiler it is 64 byte as well. So it is a trade-off. So there is a problem with the std. The problem with the std variant is there is a nothing inherent problem with the std variant, but if you try to use it with std visit, and I think we will use it because it's a very neat one, then we will have this virtual table like a dispatch. And I know there are people who don't like virtual tables, and because it is slow, not cache friendly, on all these things. So for them, they have to consider this approach. So let's say if you want to use a union, then I will say, okay, you go and use std variant. If you are using void star, you go and use std, right? That will give you a type set. And that's it from my side.